Hello, I'm Ryan from the University of Illinois, and it's a pleasure to be here at EUSIPCO. In this talk, I'll describe a sparse signal model that lets speech enhancement systems scale from small, underdetermined arrays to huge arrays with dozens of microphones. This talk deals with what researchers call the cocktail party problem. We have recordings of multiple overlapping sounds, and we want to isolate individual signals from the mixture. For example, a hearing aid could try to enhance a conversation partner at a noisy restaurant, or a conferencing system could separate different talkers in a meeting. There are two main approaches to this problem, model-based and spatial. Model-based methods rely on the structure of sound signals, like predictable notes from different musical instruments or speech patterns from different talkers. These methods can work with only a single microphone, but they don't scale well if there are a large number of sources. Spatial methods rely on multiple microphones spread apart from each other. Sound waves from different directions reach the sensors at different times, so we can tell what sound came from where. We can use spatial filters, which are sometimes called beamformers, to isolate sounds from certain directions. Spatial methods don't rely on assumptions about the signal structure, and in principle, they can separate as many sources as there are microphones. However, we need to know the locations of the microphones and the acoustics of the room. To design versatile, scalable audio enhancement systems, we would like to combine the advantages of both model-based and spatial methods. The system should work with any number of microphones, relying on signal models when there are only a few, and spatial information when there are many. Both model-based and spatial methods rely on properties of the short-time Fourier transform, or STFT. To take the STFT of a signal, we split it up into short, overlapping frames, then take the Fourier transform of each frame. That gives us a time-frequency representation of the signal. The STFT has two important properties that help with model-based and spatial speech enhancement. First, because the Fourier transform turns convolution into multiplication, we can represent the complicated acoustic paths between sources and microphones as matrix multiplications. That's especially useful for spatial enhancement because the spatial filters also become matrices. If we have a good estimate of the acoustic channel matrix, then we can design our filter matrix to invert it, enhancing the speech signal we want to hear. Here's an example of a spatial filter isolating one talker from a group of 3 using an array of 8 microphones. First you'll hear the mixture, then the enhanced signal.
People come into the borders for the beauty of the background. Is this accurate? They have no history. People come into the borders for the beauty of the background. Is this accurate? They have no history.
That filter used perfect knowledge of the acoustic channel, but we usually don't know it exactly. Here's what happens when we design the spatial filter based on a rough estimate of the channel matrix.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
That filter is less effective at blocking unwanted sound. The second property of the STFT is useful for model-based methods. Speech signals are sparse in the STFT domain, meaning most of their energy is concentrated in a small fraction of time frequency points. Furthermore, when there are multiple speech signals mixed together, their STFTs tend not to overlap very much. At any given time and frequency, there's usually only one source that is much stronger than the others. That means we can separate a mixture of speech signals by taking the STFT and chopping it up, assigning each time frequency point to one of the sources. This method of speech enhancement is called time frequency masking. The strongest source is decided by a classifier, and the quality of the enhanced signal depends on the accuracy of the classifier. Here's the example from before, but with only one microphone. The mask uses an ideal classifier that always picks the strongest source.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
Now let's hear what happens with a more realistic classifier that sometimes makes errors.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
Notice that the imperfect mask sounds different from the imperfect spatial filter. The misaligned spatial filter lets noise through, but it's still a linear system, so it doesn't cause distortion artifacts like the mask. Spatial methods and model-based methods fail in different ways. That means that we should be able to combine them so that their strengths and weaknesses complement each other. In this paper, we combine them using a time-varying spatial filter. At each time and frequency, we choose one of a set of minimum mean square error filters depending on which source is strongest. But instead of the usual assumption that one source contributes 100% of the energy at each point, we assume that it contributes most of the energy. The inactive sources are still present, but weaker. We call this the high-low model. The high-low model is a more accurate representation of the energy in speech mixtures than the on-off model used by most masks. This histogram shows the relative intensity of different sources in a mixture. The inactive sources are sometimes negligible, but not always, so we shouldn't just ignore them. To decide how strong to make the inactive sources in the high-low model, we looked at the empirical ratio between the strongest source and weaker sources for mixtures of speech signals in different conditions. Here's the high-low ratio as a function of frequency, as a function of the number of talkers, and as a function of reverberation time in the room. The ratio is remarkably consistent at around 20:1. Let's see what happens when we design a time-varying spatial filter using the high-low model. Suppose that we're trying to isolate one talker from a group, but we don't have enough microphones to perfectly cancel everyone else. A linear time-invariant spatial filter tries to minimize the long-term average square error, so it blocks the other talkers as much as possible, even when they're quiet. A mask will ignore all but the strongest source, either amplifying it if it's the target or attenuating everything if it isn't, while ignoring all the inactive sources. A time-varying filter using the high-low model also adapts based on the strongest source, but it does its best to preserve the target and attenuate all the interferers, even if they aren't the strongest source at the moment. As a result, the filter behaves differently depending on the number of microphones. For a small array, the filters can't place nulls on every interferer all the time, so they behave more like a time-frequency mask, which can help make up for errors in the channel estimate. For a large array, it can block them all, so it behaves more like a time-invariant spatial filter and is less sensitive to classifier errors. To see how spatial filtering and model-based classification can help each other, let's return to our mixture of three talkers.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
Here's the spatial filter with a rough acoustic channel estimate.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
Now here's the time-varying spatial filter with an incorrect channel, but a perfect classifier.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
We can try the same thing for the mask. Here's the single-channel mask using an error-prone classifier.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
And here's the time-varying spatial filter with the error-prone classifier, but a perfect acoustic channel model.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
You can hear that each compensates for the flaws in the other. Now let's hear what happens when we combine the imperfect spatial filter with the imperfect classifier using the high-low model.
People come into the borders for the beauty of the background. Is this accurate? They have no history.
It's not perfect, of course, but it's better than either alone. A key advantage of the high-low model is that it can scale to arrays of any size. Since this is the special session on large arrays, we tried it with the massive microphone array dataset we presented at CAMSAP 2 years ago. This array has 160 microphones spread across a large conference room, including 4 wearable arrays and a dozen tabletop devices. In our first experiment, we used ground truth acoustic channel measurements and an ideal classifier to separate 10 simultaneous speech signals. The pink curve shows the performance of the time-varying spatial filter using different numbers of microphones. The orange line is a time-frequency mask using only one microphone, and the green curve is a linear time-invariant spatial filter. The mask outperforms the spatial filter for small arrays, but with more mics, the spatial filter does better. The high-low model beats both, matching the performance of the mask for single microphone enhancement and the spatial filter for the giant array. Now let's see a more realistic experiment that uses blind source separation and a learning-based classifier. Since there are no blind algorithms that can handle 10 sources, this second experiment uses only 3 talkers at a time. The channel is estimated using geometric information and the independent vector analysis algorithm, and the dominant source is classified using deep clustering. Once again, the mask performs well for small arrays, and the spatial filter does better for large ones, but the high-low model does well at every array size. In that second experiment, we chose 2 popular source separation methods from the literature, but the high-low model can be combined with any STFT-based algorithms. Just pick your favorite channel estimation algorithm and your favorite model-based classifier and put them together. The high-low model allows speech enhancement systems to take advantage of both signal models and spatial information, and to work with any number of microphones, from the single lapel mic I'm wearing now to an instrumented room with hundreds of sensors. It can help us to make sense of sound in even the most challenging environments. Thank you for watching. To learn more about our work, please visit the Illinois Augmented Listening Laboratory website. You can also find me on LinkedIn, YouTube, and Twitter at Ryan M. Corey.